Hi guys. So as promised, this particular lecture is going to focus on solenoids. And let's see here if I can remind you of maybe something from the last video. What does a solenoid look like? Well, it looks a lot like this kind of cylindrical coil of wire that was in this YouTube video that I played for y'all last time. All right, so that being said, let's get the PowerPoint up and take a look at it. All right. Okay, so we've got our solenoid, and so again, it's just a cylindrical coil of wire that has current running through it. And as a result of that current running through it, it's going to have, it's going to have some magnetic field. The magnetic field inside of a solenoid is given by the formula that y'all see down at the bottom of the screen there. That B is equal to mu naught times small n times I. That small n is basically the number of turns per unit length. So in other words, if this coil of wire is wrapped around 500 times, and the total length that's wrapped around is, I don't know, 2 meters, then that small n would be 500 turns divided by 2 meters. That'd be 250 turns per meter. And that's what we would plug in for small n there. Now, one thing that this particular screen does not have, unfortunately, is information about what's going on outside of the solenoid. So inside of the solenoid, we've got this B is equal to mu naught times small n times I. Outside of the solenoid, that magnetic field is very, very small. It's effectively zero. So outside of the solenoid, we really don't see a whole lot of magnetic field at all. You can tell this, at least qualitatively, from the drawing that we have for the magnetic field right there. Look at the inside of the solenoid. You can see that the magnetic field lines are really tightly packed together. Outside of the solenoid, for instance, say in this region of space right here, those field lines are really, really spread apart. All right. So inside the solenoid, B is equal to mu naught times small n times I. Outside, B is basically equal to 0. And then the direction of the magnetic field is given by right-hand rule number 2. So if we look at the graphic that we've got on the screen right now, and we think about the direction of the current in that solenoid, well, the front part of that solenoid, the part that's closest to us, has the current going upwards. All right, so here it is. So I'm thinking about the particular part of this wire loop that's closest to me. It's right here, right there, okay. And my thumb is going to go upwards, and then I put my fingers inside the loop, and my fingers are directed that away, to the left. And that's exactly what the graphic says on the screen there. The magnetic field is to the left in this particular example that we've got on the screen. All right. So let's do an example problem here with this. Okay. So this example problem says that we've got a proton that's moving at some speed. It's inside the solenoid, and it's moving parallel to the solenoid's axis. It says, and then we're given information about the solenoid. We're told that the wire wraps around it 1,000 times, that the total length of the solenoid is 0.2 meters. We're given the current of the solenoid. And then we're asked to figure out, well, the magnetic field strength inside it, and also the force on the proton. All right. So the first thing I want to do, just like typical, is I kind of want to draw a sketch of this. So let me try and do that. So I can picture a cylindrical tube, and then maybe I've got a wire wrapped around like this. And I'm just showing the front part, not the back part, because we can't see through the tube, I guess. And we'll say that my current is running to the right here. Okay. So if that's the case, what's the direction of the magnetic field? I've got my coil of wire here. Let's see. I'm focused in on the part that's closest to me. That's the part I've drawn. The current is going to be going to the right, and you guys can see that part of the wire right there. That's the part that's furthest away from me. My fingers are inside that coil right now. My fingers are pointed upwards. Okay. All right. No matter how I orient my hand, as long as I've got the current going in the correct direction, my fingers are pointing upwards. Again, I realize this is not the best medium for this, but we do what we must. All right, so my magnetic field here is pointed up through the center of the coil. That's an interesting shade of color. I don't know what that is, but let's move away from that. Great, so if I've got, I've got the direction figured out. Let's take a look at the magnitude. I can figure this all out pretty quickly. Mu naught is just 4 pi times 10 to the negative 7 Tesla dot meter per amp. That small n is going to be the number of times my wires are wrapped around divided by the length of the cylinder. Literally, small n is like, I don't know, capital N over L is maybe what we could write out. And then the current is 3.3 amps. And so when I do all that, I get a magnetic field that's equal to 0.0207 Tesla. And so that's my answer for part A. Part B says that now we have maybe some proton directed this way. It's moving perpendicular, it's moving along the same direction as the axis, and we're asked to calculate the force. And we can recall that the force on a moving charge is equal to QVB sine theta. Well, in this case, the magnetic field and the velocity are pointed in the exact same direction. So in this case, theta would be 0 degrees, and sine of 0 degrees is just 0. So that means that my force in this case is just equal to 0. So that's the way it works out because of the specific geometry I picked. Now, on the other hand, if I had said maybe that, let's see if I can erase selectively here. Okay, maybe not as selectively as I wanted, but we'll work with it. If I had said maybe, well, this proton is inside the solenoid and headed that way, perpendicular to the axis, in that case, theta wouldn't have been 0 degrees, theta would have been 90 degrees, and then we could calculate the force. And not only could we calculate that force, we could also, realizing that F is equal to ma, and then what have I got here? I've got something moving around in a circle. F is equal to mv squared over r. I could calculate the radius that this thing moves in. And that's actually what we asked you to do for one of your problems, one of the more complicated ones that we gave you guys this week. All right. So let me clear all that and we will see what's next. That's the sheet of paper I was supposed to be working on. My bad. All right. So here's something for y'all to check out on your own. I'm not going to get into it, but why do we care about this idea of solenoids, magnetic fields in general? There's all kinds of medical applications. One of them is an MRI, magnetic resonance imaging, which can tell us what's going on inside of our head in this example, or inside of our body in general. Some of you guys have experienced an MRI. It's kind of confining, boring, loud, but also vitally important to the medical field. Basic structure here is that of a solenoid. By changing the magnetic field that the human body is exposed to and looking at some signals from the human body, we can develop this internal picture, but I'll let you dig into that on your own if you're interested in it. Okay, the last thing we have here is we introduced the idea of a current carrying wire generating a magnetic field. Well, that's great, but that doesn't really explain what's going inside of maybe a physical magnet. So the reason why a physical magnet actually has a magnetic field is because of the spin of the individual atoms in that magnet. So if we've got a ferromagnetic material, ferromagnetic material is going to have a bunch of unbalanced spins because of the way the electrons fill into the electron levels. So something we might have looked at in chemistry at one point. 1s, 2s, 2p, 3s, 3p, 3d, so on and so forth, all those electron levels that maybe we had to fill in at some point. So ferromagnetic materials have a bunch of unbalanced spins that all point in one direction, and as a result, we can end up with kind of microscopic areas inside of materials where all the spins are lined up in one direction with it if we focus in on adjacent atoms. That's what we've got on the left-hand side of this particular drawing right there. We've got a whole bunch of what are called magnetic domains where the spins are lined up in the same basic direction inside those domains. What we can do with this unmagnetized hunk of iron now is bring a really strong permanent magnet near it, and that will cause those a lot of those magnetic domains to realign, and will magnetize that magnet. Well, great. Well, how do we get a permanent magnet in the first place? Well, there are some in nature, but maybe the simplest way we can do this is just with a solenoid or an electromagnet, run a really high current through a solenoid, and then we've got our magnet that we can use for further magnetization. Or we can have a nice strong magnet that's been polarized that way to start with. Whatever, don't worry too awful much about that. But anyway, this is what the microscopic picture looks like inside of magnets. All right, I've babbled enough. Awkward pause.